In this video, I'm going to walk you through a couple of the basic calculations for the section on fasteners and fastened joints. So hopefully you've watched the lecture series on that, and you will have seen a lot of excerpts from Machinery's Handbook in that lecture. So here I'm going to try to show you how to use some of them on a sample final exam question. This question, for instance, came from one of my final exams that I've given in the past, so I thought it was a pretty good candidate. The question is pretty straightforward, and most of this information is really just going to be basic formulas and multiplication and division. The question is going to be how easily can you find all the information in your copy of Machinery's Handbook. So hopefully we will cover all of that in this video. So we'll start with the first one. What is the tap drill size for 70% thread using a cutting tap? And a cutting tap is really the most conventional kind of tap. So we would come over here to threading, which is the little insert here. And when we look at the section on threading, it doesn't take us long flipping through it before we get to the section on tapping and thread cutting. Under the section on tapping and thread cutting, it says here tap drill sizes, page 2029, and that's pretty easy for us to get to. So we pass a bunch of charts on recommended size limits, but none of those charts give us the ability to factor in percent of thread until we get to this formula right here, which gives us the basic major diameter and then gives us a number to subtract from that to find our desired hole size. So if I enter in some of the information here, the tap drill size for a 70% thread using a cutting tap for a 5/16 24 Unified National Fine 2A fastener. So here we want the basic major diameter, and that's 5/16, which is 0.3125, minus 1.0823 times the percent of full thread, which is 0.70 because we want 70%, over the number of threads per inch, which is 24. Pretty simple. We can bust that out on our calculator. Everybody remembers their order of operations. And we get 0.281 if we round to 3 decimal places. Okay, so that's our tap drill size for the cut tap. B asked for the same calculation, this time for a form tap. So now we need to keep going through our section on threading until we see the discussion on forming taps. So we get through some of the other standard sizes here. Oops, I think I passed it. To the section on cold form tapping. So those are the form taps that we discussed in lecture. And they again give us a really simple formula down here. If you just read through this section, they'll talk about how to find your tap drill size for a forming thread. But there is one issue here. This seems to crop up every semester when we use this, and it's worth talking about. These books are written by a number of different people, and obviously the person who wrote this formula didn't really talk to the person who wrote the other formula, because there's a very distinct difference here that will throw off your calculations. In this formula, this person expects you to use percent of full thread as a whole integer, not as a decimal number. So when you fill this out and you're looking for the theoretical hole size, the basic tap outside diameter, which is the basic nominal diameter, minus 0.0068 times when they say percent of full thread, and we look at our question here, 75, you just write in 75. It's not 0.75. It's really confusing. I don't know why they do it. Maybe it hasn't been brought to their attention yet. And then this is over threads per inch, just like before. So again, we can enter in everything that we just did, and we get 0.291 as our tap drill size for our form threads. Now, it's not particularly necessary in this course unless I ask you for it. But since we're giving a demonstration, these numbers don't really do you any good if you're drawing a print. Because if you tell your machinist to drill a 0.291 hole and that doesn't line up with any standard type of drill, then they're going to tell you got to buy a custom drill. So it would help, since this question does indeed call for the tap drill size, the size of a conventional drill, for you to go into the section on standard tooling and find out, well, what are the sizes of drills that would come in, that would come close to that. So here in my book on 889, we should find a section on standard twist drills. And I have here maybe just before 889. Yeah, just before 889 we have the standard ANSI straight shank twist drills and all the different series they come in. And we haven't talked about it in this class because I assume you would get it in your machining class. But drills come in many different series. In the American system, they come in fractional, letter, and number. And then in metric, obviously, they're in metric system. But it's important to note that when we call out different standard drills, that they come in those three series. So if we look down through this chart of drill diameters, we see that a nominal drill of 0.281 is not a fractional size. It's not even a metric size, but it is in the American system as a letter K drill. And then similarly, if we keep looking, 291 is not a size in anyone's system, so the next closest would be a 7.4 millimeter, or we'd be awfully close to a letter L. Now, that's not really relevant to this class, but I put it in there because it's a demo, and you may need that for work at some point. So, now that we've done the tap drill size calculations, let's move on. The last four are really concerned with fastener strength. So we're kind of outside of the thread cutting stuff now, and we're into fasteners. So the first one is the tensile stress area. And if you remember from our discussion on tensile stress area, that was the area of thinnest cross-section in a fastener. So it's where we're going to find failure anytime we stress a fastener to its maximum. So if we think about a thread form, we have this 5/16/24 Unified National Fine thread form, and we want some information on it. So we go to the unified screw threads. We come down here, there's the coarse thread series on page 1844, fine thread on 1845. So if I go there, what I find is they have all kinds of relevant information about major diameter, minor diameter, basic pitch diameter. But over here on the right, there's a column for tensile stress area in square inches. And that's going to be pretty relevant to the next few questions. So I'll come down here. Notice I'm in the fine thread series, right? Because I have a fine thread here. So just to verify, a 5/16 with a 24 pitch has a tensile stress area of 0.0580. And that's inches squared. So it's not something you have to calculate, it's already done. And I hope that you're able to find that table easily. So on to the next question, D. What is the ultimate tensile strength in pounds? And it doesn't say the ultimate tensile strength in PSI, it just says in pounds. So we got to keep that in mind when we answer this question. But ultimate tensile strength is going to be referring to the material that the fastener is made out of. And this is an SAE grade 5 fastener. If you remember from the lecture, we talked about head markings. And the grade marks are going to tell us what the strength of the material that that bolt is made out of. And that's page 1534. So if I flip over to 1534, then I see here my SAE grade 5, right, which would be marked by these 3 lines like you would see on the head of a bolt, for sizes 1/4 inch to 1 inch, has a minimum tensile strength of 120,000 psi. So when we talk about designing something, we want our ultimate tensile strength to be designed for at a minimum of 120 psi, 120,000 psi. That's the ultimate tensile strength, but that's the ultimate tensile strength in psi and not in pounds. We want to know when you apply this 120 psi to a fastener of this size, how much strength can that fastener hold? And you may be tempted to multiply this times the area of a 5/16 bolt. But remember that the area of smallest cross-section is the tensile stress area, which we just found right here before. So the answer to this question really involves multiplying these two numbers together to tell you when you apply this tensile strength for the material times that minimum cross-section, how much weight this bolt can hold up. So 120,000 times 0.0558 is 6,960 pounds. So for a 5/16 bolt, that's really not bad. That is the absolute maximum ultimate strength that we can design for, because it is the minimum strength for any fastener that we come across. So that's our ultimate strength there in pounds. Now the next two questions relate to preloading the fastener. And when we talked about this in lecture, I said that in order for a fastener to do its job, it has to be torqued to a certain preload so that the right amount of friction can be applied to the body of the fastener and to the fastened joint. When we open the section on fasteners, the very start is about tightening bolts and wrench torque, which is the last two questions we've got to answer here. So if I just flip to the very beginning, you'll see here, and this is a section I have outlined in your lecture, that when it comes to determining preload tension, we have two formulas here. One is for reusable connections and one is for permanent connections. And I've specified right here in the question that I want you to find the preload for use in a reusable joint. So if we look at our formula here, here's the formula for reusable connections. And this is for E. This is F equals 0.75 times A sub T times S sub P. And when they talk about A sub T and S sub P, they say here that A sub T is the tensile stress area of the bolt, which we just found, right? 0.0580. And then S sub P is the proof strength of the bolt. Now the proof strength is a little bit different from the ultimate strength, so we want to go back to our grade marks on 1534, go back to that grade 5 fastener, and now here for that grade 5 fastener the proof strength is 85 ksi. Okay, so now it's just a simple multiplication problem. The amount of preload tension we want is 0.75 times 0.0580 times 85,000. And that gives us 3,697.5, and that should be pounds of preload tension. But now how do we get that 3,697.5 pounds of preload? Well, we have to use a wrench in most cases. And so I've asked you here on the last question, F, what is the wrench torque required to reach the calculated preload? If we look on the same page that we just talked about the preload for reusable connections, if we come down a little bit, it says right here, the torque necessary to tighten the bolt is estimated using the following formula. And that formula is T equals K, which is a K factor, times F sub I times D, where T here is the wrench torque, K is a given constant, which for the description written here, that given constant is 0.2. F is the preload tension, which is 3,697.5. And then D is the nominal bolt diameter, 0.3125. So we can multiply all those across. 0.2 times 3,697.5 times 0.3125. And what we get is 231.09. But we have to think a little bit about what those units are, because we need to apply units to our answer here. The K value is unitless. The strength, or the stress, the preload stress, is in pounds, and then the diameter here is in inches. So this is, in terms of torque, this is in inch pounds of torque. That's the preload wrench torque. So if you had your 3/8 drive ratcheting torque wrench, you would set it for that value, and when it notified you, you would have torqued the fastener to the correct preload torque. So that's the basics of applying some of what we talked about in the lecture to what I expect you to have the knowledge for on the final exam.